Well, I think it's hopefully this will be good. The competition of just sitting outside is really severe today. It's really tough. Okay, so but hopefully you'll get a chance to do that also. So this is a replay of somewhere where we were 2 years ago in this course. So I'm using this. I guess when I found I made this on my laptop, which is at home, so I couldn't change it easily to 2005. But you can survive that. This stuff is a little bit like Latin. It doesn't change all that much, right? It's not that topical. It's not dependent on the latest developments. What I'm going to talk about, so we're actually shifting, and actually there might be a slight gap in where you are and I am, because the homework is up to you mostly. So if you're doing the homework, you might still be working on renewal processes, which is supposed to be done today, but turned in Thursday. So you may be still in chapter 7. So I'm shifting to chapter 10. It's the last topic, Brownian motion. And this is the one topic that connects. If you're interested in finance at all, this connects nicely to finance, because this is connecting to stock prices and options and things like that are in here. So we're going to do a little of that. We really have just time is running out, right? Time is running out. We have, I guess, this week and next week. So we have 2 weeks. So I'm thinking of this as like 3 classes. Maybe there's some review even on a week from Thursday. So we're doing chapter 10 now in these last classes. And this particular stuff, this thing, is this is from chapter 1 of my book, 2002, online. Actually, the whole book's online, but what you can easily get to, so if you're on my web page, you could go to somewhere you'll see book, and there's part of it's online. So certainly this chapter's online. Actually, the rest of it's online someplace, but not advertised, because the publisher required that only part of it be online. But actually, I can, if one were interested. So this is actually connecting to what I've shown restraint. We have not made that the required textbook for the course, right? That's what would be a natural way to sell a few copies of this book, would be to do that. Anyway, there it is. This book is called Stochastic Process And actually, the first chapter's got this title, I think, if I remember correctly. I've kind of repressed the whole thing, but it was fun doing it. So this is the title of the book. Sort of the idea of this chapter of the book, and the idea of, well, the book is about a lot about limits, and we're not really talking about that much in this course, but it plays an important role in Brownian motion. And so maybe I'm going through. It may take me all 3 lectures just to go through this thing if I go slowly enough. But maybe if we parse the title of the lecture as it's described there, experiencing statistical regularity, the statistical regularity part has to do with the stochastic process limits, that there might emerge statistical regularity in these limits, and the experiencing part is that my approach to this book in chapter 1 is that you should which I would suggest you should do for everything that we've had so far, is in order to experience the theory that's being presented, it would be great to simulate it and do numerics. And the idea here is that the first chapter just talks about experiencing it. So what I'm going to do is do some of that for you now. We'll just look at it. And in the background, in the book has the same stuff. So it's actually a kind of a summary of part of the chapter 1 of the book. Okay, so we're going to do it this way. I wonder if lighting's probably all right. Would it be better if is this that better? Maybe better. Maybe better. Yeah. Seems like a good combination. Okay. And I've got this, and I'm supposed to use this, so people in Cyberland can follow this as well as you. So instead of jumping up and down over there. Okay. So, in particular, what we're going to do is look at random walks. And I guess in the spirit of the stock prices, what you should think about is you're looking at daily stock prices, and you're at some value, and every day you take a step and it moves and it has some new value. So you're looking at a sequence of stock market prices, and there's an increment. So what you see is the sum of the changes. So you think of the steps are the changes in the stock price, and the actual value you see is the partial sum of all those changes. And that's one simple view of stock prices. There's actually a more complicated view, which we'll come to. So the thought is, the idea is that a random walk is a really basic stochastic process. It's discrete time. You just think about the random walk, but instead of being bombarded with theorems about the random walk, you just simulate it and plot it and think about what you're seeing. So that's what we're going to try to do. That's the objective. Okay, so to put things in perspective, here we're reviewing the whole course. We started by doing discrete time Markov chains, which have discrete time and discrete state. We went to continuous time Markov chains, which have continuous time but still discrete state. When you go to random walks, the random walks could have continuous state. In other words, you no longer have to, you're moving along in discrete time, but these increments don't have to be integers. So the stock prices could be measured in whatever units. I mean, maybe they're actually, you're not arbitrary, but you could have continuous state. And then if you have a random walk and you have a lot of steps, time might as well be continuous. And that's where we're headed to. And the idea is we're going to do simulation experiments, and these are really easy to do, so you could easily do this. This is takes 5 or 10 minutes to do all this stuff. You just sit there, the code, 3 or 4 lines of code, you can simulate random walks very easily, but there's really a lot to see. So in a little bit of simulation, you could actually see whole books full of theory. And it's actually much more interesting to see it actually happen. And especially if you're here, you're interested in the combination of the theory and the realization. So I'm just displaying some of this, but it's really fascinating. But the point is, you have to think about what you're looking at. Okay, so here's random walks. We've got IID random variables. Those are the steps. X1, X2, so forth. Standard situations, steps. Then we form the partial sums. We start off at 0, and we look at the nth sum as the sum of the first n random variables. And we just plot the stuff. We plot the random walk. The first n, starting at 0, so n plus 1 steps. So to start with, we're assuming down here that each of these steps is uniformly distributed on 0, 1. Now, there's no real good reason for choosing that. It's just one distribution. The one reason for choosing this uniform is that's the easiest thing to simulate. When you do a simulation, pick anything like MATLAB, you just generate random numbers. The thing it will naturally do, just generating random numbers, will produce numbers uniformly distributed in the unit interval. That's the standard, simplest random number generator, produces numbers that are approximately uniformly distributed in the unit intervals between 0 and 1. So therefore, the easiest steps are just to let those be uniform. You don't have to do anything to change the distribution, to make it exponential or make it normal. You don't have to do anything clever. You just get uniform numbers easily from your random number generator. So this is what you would get easily. The reason for choosing this is it's the easiest thing to do on the computer. In any language, you can generate uniform random numbers. So then each step is uniform. It's between 0 and 1. So now you've got to think a little bit, well, what's going to happen, right? You're going to plot this. It's actually initially boring. Hopefully I persuade you it's sort of interesting as you start looking at this further. So I guess I'm about to say that. But the thing you should be thinking about is in your mind, what do you expect to see? You're going to plot n steps. Boring. But I mean, this is what you should see. Well, it should go up, right? It should go up because, so I've plotted for n equals 10. I plotted this random walk for n equals 10, and the random walk, remember, is the sums of the uniforms. So what do you see? I mean, you see that you start at 0. That was part of the condition. And every step goes up because the steps are between 0 and 1. So they go up. And since the average step is a half, right? Uniform between 0 and 1, the average step is a half. So after 10 steps, you expect to be about 5. And, this is just a random thing. And there was a big step here, and there's a little step here, and so forth, right? So some steps are going to be nearly 0, and some steps are going to be nearly 1. If any step's bigger than 1, there's something wrong. I made a mistake, right? So the steps should be between 0 and 1, and they're going to be somewhere up around 5. If you could, by chance, have everything come down here and all the steps be small, or you could have all the steps be large, right? In the end, you could be near 0 or near 10. It's just as if you flipped 10 coins and you got all heads or all tails. It could happen, but not very likely. Okay? So this is what you see for just picking n equals 10. So you're plotting random walks. In case to orient late arrivals, this will be a quick orientation of late arrivals. We're going to go through this fast. We're going to experience statistical regularity by looking at random walks. So we're plotting random walks. We're going to do simulation experiments. We're going to plot a random walk, which is the sum of IID random variables, and the steps are all uniform. We want to know what we should see. Here's what we do see when we plot 10 steps. A random walk, steps are uniform, you're going up. You don't see anything particularly interesting. Now, the point of this stochastic process limits, the limits is what happens as you look at this random walk and you take more steps. And what you want to see is some sort of regularity happens. You want to begin to see that there's really, because of large numbers, things are going to be regular and happen in a systematic way. And some of these systematic things are obvious and some are a little less obvious. Okay? So if we look at larger sample size, what will we see? So what should we see? Suppose we looking at these, well, also S0, starting off at 0. But suppose we look at powers of 10. So the number n, the number of steps is some power of 10. So we're looking at 10, 100, 1,000, and 10,000. And here's what we see. This was a replay of what we saw before. It's going up. It's going between 0 and 5. Already when n is 100, things look kind of regular, and then as it gets to 1,000 and 10,000, it's totally regular. So it should be totally obvious what you would get if, suppose, we did 100,000, or 1,000,000, or 1,000,000,000, what the plots would look like. Now, part of this, I mean, the point is, I guess the point of this a little bit is, this pictures, if you just look at these pictures, you see the pictures all become the same. That's the thing you're supposed to see. That's what the math tells you, but in a way that you might not recognize. The pictures all become the same. And actually, all you do is you don't do any math. There's no math at all. You just plot. You're using the computer program and you plot. You plot the sums. There's no math, no processing. No processing whatsoever. The code just says enter, n, pick n, and plot S0 through Sn. That's the thing, 3 or 4 lines of code. Generate random uniform numbers, do a cumulative sum, and then you've done it all for a vector, so it's like you got a vector of cumulative sums, and you just plot it. So the only thing you're doing is plotting. I'm not showing you, I'm not doing any mathematical analysis pre-processing. I'm just plotting n steps of the random walk. The point is, this is totally raw, direct. You plot the random walk, so this is just what happens. You plot the random walk, and it looks like this, and it looks regular. So down here, when you have n sort of large, it's clear in all these plots that the maximum value is half n over 2, right? There isn't, when you get to 10,000, there isn't one of these, this doesn't jump all over the place. You're going to have the number, this random walk is moving like a straight line up here to n over 2, which is just the law of large numbers. It's the law of large numbers. It's telling you that the average step is a half. And in the average, that's what you're going to see. It's telling you the law of large numbers is operating. And it's operating not just at the end, but the whole path is a line. That's actually what's meant by a stochastic process limit. The whole random walk in this picture has gone to a line. Not just the average, Sn over n, going to its mean, but the whole random walk, the whole thing goes to a line, right? You see the whole random walk, we just plot it, and there it is as a line. However, there is something going on here that's in the plotting that is happening automatically. In other words, I just plotted it, but the plotting is doing something sensible. Well, I'm sure that's what I'm saying next, if I can remember from 2 years ago. How does the plotting work? So this becomes a central feature. In other words, all we have is a random walk. And if there's all that stuff going on, that it looks nice, all the pictures become the same, what's going on is in part in the plotting. But the plotting is just what the computer program does, but it does something very sensible, which is what you would do if you looked at the random walk and had to do it mathematically, but it's more sophisticated then. In other words, it's going to scale. The program automatically scales the random walk. If you didn't have the program do that, you would have to think up how to do this yourself when you do the math. So this is part of the math. Okay, well, let's think about what it does. In other words, when you think about what you see, in the way I've done this, let me go back to this. In this picture, you can hardly read the units on the axis. That's deliberate. What you really see is you see some sort of rectangle and a line in the rectangle. And that's the thing that is the thing that you should see. That's the important part. Actually, the units are changing in all these graphs because there's more and more, as n increases, there's more and more steps and larger values. So the units on the two axes are changing from figure to figure, and yet what you directly see when you do the plot is a line. It is approaching a line. The units have been adjusted, but that's done automatically, and that's done because the plot program, fits the data into this rectangle, right? And if you forget the shape of the rectangle, you can think of it as a square. Unit, 0, 1 on one axis and 0, 1 on the other axis, right? So you can think of it as a square. And so this is now getting mathematically, now I'm sort of writing down here mathematically what the plotter is doing. I'm not telling it to do that, right? The plotter is just the program, all these plotting routines do. They fit horizontally to create a function on the unit interval. So if you have n plus 1 points like S0, here's y0 to yn, it kind of, let x be a function from 0, 1 to r, and x of t is y of nt, where this is the greatest integer less than z. In other words, all this is saying is, if you've got n plus 1 points, they're all jammed to fit in the unit interval. Time is contracted by n in order to fit n points there, right? So if you increase the thing if you multiply by n again, they'll all be more and more points in the same space. But now I'm emphasizing, so far this is only emphasizing horizontally. If we continue, if we fit vertically, we make sure that the maximum value appears at the top and the minimum value appears on the bottom, right? That's all that's happening. So this is some fancy math to say that. It says, well, suppose you have a function x is given. What does plot do? Well, there's the infimum, the supremum, and the range. In case these words are not familiar, infimum is the smallest value, supremum is the largest value, and range is the difference, right? So infimum is the smallest value, supremum is the largest value, and range is the different. And what is plotted is what you see minus the smallest value divided by the range. Whatever it is, it's replotted that way. Those two, so horizontally and vertically, it's rescaled. So it fits there. So then, because of that, that's always going to produce that line. And so as n's bigger, you automatically, otherwise you'd have to say, what do I have to do? I have to jam the point. If you did it without plotting, you'd say, well, how should I scale all this to get the thing to come out right like a line? You would want to say, in a theorem, you would want to say something like, you would want to write something like this. This function, the steps, as a function of, this is kind of that funny thing, this whole function of t goes to this constant function of t, which you'd want to have happen. But you would figure out all this scaling, intellectually for yourself, that you wanted to scale to n, and you'd figure this out, and you'd say it's going to a line. And you might, if you want this to be, somehow it's in the unit square, you're going to scale by this somehow. And you're going to get this. So you're going to divide by the mean. And you're going to get this to go to this, because it's going to fit in there. Because whatever it is, if it's in a unit square, it's going to look like this. Because if it's going up as a line, and it's fit in the unit square, the line that fits in the unit square is got slope 1. In the picture, what you actually see, if you think of it as a unit square, these were only rectangles because of the number of plots I put there on the page. If I plot 2 by 4, if there's lots of them vertically, then they're going to be flat rectangles. If I plot only one plot per page, then it'll be square. So it's just a question of what I'm doing. Okay, so when you plot a random walk, this is some thoughts. When you plot a random walk, you get a random plot. In other words, the random walk, those steps are random. If you do it many different times, every time you're going to get a different sample path of that random walk. But that random plot that you get is a random function. And it's a random function mapping the unit interval into the unit interval, because that's what you're going to see. And so you get a stochastic process, so all of this course. You plot the random walk is a stochastic process, but when you do the plot, it's actually continuous time. And as it becomes, those pictures you can see become continuous time. Okay, so you think, well, for 100 and 1,000 and 10,000, if you were to make a mathematical model of what you see, the mathematical model would naturally be continuous time. Not for n equals 10, but for all the other cases, it would seem the most direct thing you see, it looks continuous time. Just thinking of what you're looking at. Right? It isn't, it's discrete time, but because it's times being mushed together, it looks like a continuous time process. Okay, now actually things are supposed to be getting more interesting. Okay, so now you're supposed to think of another experiment. In this experiment, okay, this is where you want to engage. We're now saying, suppose we do a new experiment, and suppose instead of making each step uniform, we make the step uniform minus a half. Now, we're subtracting a half because that was the mean. So when we add mean a half, and it was not, just plotted the sums of the uniforms, the thing ramps up, right? Just ramps up. So we get that line. So now I'm going to say, well, let's subtract that. So there's the random variable now has mean 0. I've just subtract the mean, and I plot the thing. So now I've got a centered random walk. Now it could go down as well as up. But in some sense, the long-run average should be instead of at 10,000, instead of the sum being 5,000, it should be about 0. because we've subtracted 5,000 from that thing. So the thing that you want to think about, please think about this, engage about this. This is probably the key point. You want to think about, well, if we're going to subtract 1/2 from every step. Before, we saw line like this with a slope 1/2. Now we're going to subtract 1/2 from every step. So before it was like this, now what? Okay, so here's what we see. So the question is, are you going to see, is this what you're expecting? Yeah, you should. Somebody should frown. Thank you, Thomas. You frown. At least you were thinking. So the thing you should have been thinking, the first order thought is, okay, it's going to be a horizontal line now. That's the first thought, horizontal line, right? Because it was a line going up, and now you're going to subtract the slope as 0. But why not? Because it's rescaled to be the maximum. I mean, it would try to be a horizontal line, except that it's always going to plot the maximum and the minimum. And now, since its mean is 0 in each step, the mean value is 0. The expected value of every position all the time is 0. But it's actually randomly fluctuating about that because it's random. So you don't see, it isn't this, it's going to give you the largest value you get. So here you see you actually, if you subtract the mean, it only goes up to 1.2 and it's moving around, but in this case it's all positive. But here it's going from, in the case of 100, it's going from minus 2.5 to minus, is that more visible there? Minus 2.5 to 0.5. So 100 steps, it's not going very far, is it? Well, it's uniform between 1/2 and minus 1/2. It could go down to minus 50. It could go up to plus 50, right? So it's now between, it has to be between minus 50 and plus 50. But actually, it's got mean 0. So it's going to be fluctuating about 0. This one, here's 0 is somewhere here. It actually, this one spent most of the time below 0. This one spent almost all its time above 0. This one spent a lot of time above 0, then below, and this one starts at 0, goes down. I mean, this one's good. You start to stare at this one. So you think of these. You take this one, 10,000 steps. 10,000 steps, just like the stock market. This is where it gets good. These pictures are just like the stock market. That's where the connection. You should start thinking, now where have you seen pictures like this before? This one looks like last week's stock market price, if you think, right? If your last week looks like this, right? Last week is something like this anyway, right? This, I always used to relate this to my experience at AT&T. That's last week is nothing compared to AT&T over the last 10 years or whatever. Anyway, this part here, or Lucent. Lucent had a spectacular thing. Lucent was even, after 96, Lucent at one point went from 98 to under 1. This stuff looks nothing compared to that. Okay, and then of course, if it's your money you pay, this stuff really has all sorts of meaning, right? If this is stock market prices, it's all, okay. So you see this one and you think, oh, this one here, you think, surely we made a mistake in the simulation. The thing is systematically going down. Yeah, that's a thing you'd wonder. Actually, no. But I mean, yeah, it's possible. Is it possible I could screw up? Yeah, okay, that's certainly possible. But so the question is, are these reasonable, right? So there's initial reaction is, well, what are we seeing? Why are we seeing it? And is there are errors, or is it really just exactly what we expect to see? That's kind of the point. What do you expect to see? So in part, the first thought is it's totally reasonable to get focused on what you see the first time when you just plot the sums and they're going up, to expect to see a horizontal line, because that's the sort of what's the first order thing is that to the overall averages. But the reason is these plots are showing much greater detail. they're rescaled vertically, automatically, to have a totally different vertical scale than they had before. These would look horizontal if you plotted them in the same vertical scale. If you deliberately fixed the vertical scale, these would look flat, totally flat. This thing here in 10,000 is going between 0 and 60. Before it went from 0 to 5,000. Right? This went before, when we plotted the thing before, it went up from 0, as you go from 0 to 10,000 this way, it went up from 0 to 5,000. Now it's from 0 to 60. So the scale is reduced by 100 times, more than 100 times. Well, then you see this stuff. Okay, well, you might think, one thing about this thing is you might think, well, let's suppose we repeat this. This experiment we only did once. What happens if we repeated it? Just to see what we might see. So that's next. A lot of points. I think it's working. Hopefully it's working. See, the little hourglasses here. See, there it is. So this is 6 experiments repeated with n equals 10,000. This one looks like that last one, right? It's going up, systematically going up. Things look better, right? Things look better. You can start staring at one of these and think about their systematic properties, right? Well, we did this 6 times. Now, the question would be, here's another interesting question. So I don't know whether, you've probably seen more interesting pictures in your life than these. But at any rate, these are at least a step more interesting than the first ones in the lines. Okay, so the thought would be, well, here we did this plot. Here's 6 plots for 10,000 steps. What would we see if we plotted 1,000,000 steps? How would the picture look different? Suppose, remember, these are 6. All it's done here is you take that centered random walk, you construct the vector just in MATLAB with one line, cum sum on the thing, and you've got these sums, and you plot. You don't do any processing. No processing, just plot. Simple construction and plotting in 3 or 4 lines of code. And, okay, there it is. And then you think, well, what would happen if we now took and did, instead of 10,000 steps, we did 1,000,000 steps? Can you, do you have an expectation of what you're going to see? And is there something to be said about what you see? So let's do that. That's going to take a while longer, although not so much. It should be the same because of the way this is constructed. But this is now, you can't see it very well, but the units on these axes this now goes to 10 to the 6 instead of 10,000 on each graph. So this is 6 repeated experiments, but this now goes from 10 to the 6 on here on this, and then the top is going somewhere. I mean, you could start paying attention to what the units are. But what is the thing that you observe? What should you observe about this and the previous pictures? And I mean, there's something to think about this. This is sort of like anything you did if you were to do a physics experiment. I mean, imagine you were potentially discovering gravity. You drop the stuff from the tower, and you see that you drop stuff, and you see that somehow the time, certain things are the same. There's certain patterns, that there's regularity in the world. Just like, I don't know, whatever it is, regularity you observe in your life. The food at Carlton is systematically bad. The food at John Jay is systematically bad. There's a chance to observe stuff that has some sort of scientific, engineering, mathematical thing. There's regularity, and you should pay attention to regularity when things are the same. The simple thing I want to emphasize, the obvious observation, is these figures, these plots, look just like the ones with 10,000. That's the first order thing to see. Not to see, well, this one has this hump in it here, and therefore it's a little different. Or look at these ones, have a bunch of them going down, so maybe now when you make more samples, they start going down more. Yeah, you can look for you can look for stuff like that, right? You can sort of see what's there. Look at these. A lot of these go down. Maybe it's eventually going to go down in some miraculous way. But if you kept doing this, then you'd say, oh, I'll look at 6 more, right? And then you'd see they going up, and you'd say, oh, well, forget that one, right? But the obvious thing is this. If you didn't see the units, this could have been the same picture as before. And the thing isn't just a line. It's some mess. But you get the same mess. You get the same mess no matter what n. So if you make n 10 to the 8, 10 to the 10, and so forth, you're going to see the same picture. Same picture for 10 to the 3, approximately. Almost looks the same for 100. Remember, this is back to, we could go a couple of these, just may jump back. Here we are back to this. Right? I mean, n equals 100 here is sort of the same sort of thing, and here's 1,000. I mean, it's really the sort of same thing. This doesn't look, on this picture, you're struck by the fact that 10 is very different than 100, and there's more, the density of the points. The bottom two look about the same, right? But it's a little odd, but when you go forward and you do more of these things at larger values of n, you see that this regularity, that the picture all looks the same. Here's the 10 to the 4th case again, and here's the 10 to the 6th case again. Okay, well, I mean, the obvious thing that must be going on is you're seeing a stochastic process limit. Now it's kind of interesting, because each time you start with the random walk, and the plotting automatically scales it in such a way that you're seeing that the random walks, no matter what n is, once you do these centered random walks, they actually are wiggly, and they're random. They're not going to be just a line, and yet it's the same in some sense, independent of n. In other words, what you should be thinking is, if you did this experiment for some value of n between 1,000 and up, any value of n, and you repeated it, it would look like one of these plots. Which one, you don't know, because they come out randomly. So you're seeing a stochastic process limit. The thing is seeing it, and you're seeing the regularity at the end. The statistical regularity is there is something that describes these things for large n that's still meaningful. In other words, each picture is different from the other. I mean, this is essential what this course is about. The world is full of randomness, which is disorder and confusion, right? Randomness is confusing. You want to understand randomness. You want to see that these pictures, though they're individually different, they all are possible realizations of the same random thing. You can think there's a random picture. The random picture in any one of these for any n gives you the same random picture. And you'll do this experiment and you'll see something like one of these. And sometimes they look a little more bizarre than other times. Sometimes they all go up, sometimes it goes down, sometimes it fluctuates a lot. But once you've looked at about 50 of these things, you kind of know what to expect. And you can tell these pictures from a lot of other things, because they'll have, you know what they look like. Okay, so the obvious thing is this thing you're looking at is Brownian motion. That's what chapter 10 is about. It's what you're looking at right there is Brownian motion. These pictures are pictures of Brownian motion. One of the important properties of Brownian motion is that when you rescale it, like the plotter's doing for you automatically, when you rescale it properly, change time and space in the right way, you get the same thing back again. It's got self-similarity. It's like those weird Mandelbrot fractals, only it's an easier version. Okay, you know what weirdness, but this is actually, there's a lot of weirdness in this process, actually. If you start to study it, it's really bizarre. Like the paths in this thing of Brownian motion, of course, these are actual plots of finite things. But the theoretical limit, because it's sort of complicated, has the property that these paths, as you see, are continuous. But as you might guess from looking at these pictures, the paths are nowhere differentiable. That's a little tricky to prove, but in fact, the derivative exists nowhere. Because everywhere rescales and there's in this whatever time scale you look at, if you expand a small amount, that looks the same thing, and there's lots of fluctuations again, and the derivative isn't regularly enough to define. So actually these paths, the limit that you talk about, is a peculiar process, but it has regularity in a larger time scale. So the fact that the derivatives don't exist is a little bizarre, but it doesn't really bother you when you look at these pictures. Now, this and these things, the other thing is, what does this connect to? These pictures obviously look like the plots of stock prices, which is why the chapter is partly about modeling stock prices. The model, these pictures are these are the kind of models people make up when they're modeling stock prices. Sort of looks like that, right? So I mean, that's sort of natural. Okay, let's boogie on. Okay, let's see. So to beat a dead horse into whatever, combine bad metaphors, whatever, but anyway. Okay, so you see Brownian motion. Okay, one approach to Brownian motion. You see Brownian motion. Okay, so density estimates. So I guess the thought is, well, let's look at the distribution of the last position. So you do this random walk and you say, well, where am I at the last step? And now you're asking a different question, but you should have an opinion. You're looking at the distribution of where you are at the nth step. It's the sum of IID random variables. Summed by the central limit, the sum of IID random variables should be normal. So the distributions of this plot, the increments should have some sort of normal. There should be some normal stuff going on. So you can just plot, do a probability. You take S. I was doing this in S. You just plot a density estimate of the partial sum. So this is what you get. This is looking at the 1,000th sum. So you let n equals 1,000, and you subtract the mean as before. So it's centered. You've done the case of the centered case, and you've let n be 1,000, and then you do 1,000 samples of that one case. You're looking at the Sn, S 1,000 minus 500, and you do 1,000 samples of it, and you plot it. And then you say, oh, if I didn't know the central limit theorem, I'd think this looks sort of normal. I mean, you could make something out of that weirdness at the peak, but there's only 1,000 samples. So then you do more samples, or fewer samples. So you sort of see, well, oh, if I do 100 samples, I see the thing I see this. 1,000 samples, I see something like what I saw. 10,000 samples, 100,000 samples, looking pretty convincing, right? Yeah, hopefully the pictures are really important. The proper final that would screening, you should all take elementary final 1. Elementary final 1 would have a picture of this with A, this is the exponential distribution, Poisson distribution, normal distribution, right? A, B, C, D, whatever, right? So if you thought the exponential distribution looked like this, that would be screened out, right, for special abuse, so that you'd recognize this is the normal distribution, right? And you'd sort of, if you have thought about the problem and you have expectations about what you see, you will see, in this case, with 100, you will see the normal distribution. Even when there's total nonsense, if you have, this is where, of course, it gets crazy. If you know what you want to see, you'll see it. Maybe, right? So this is a little ambiguous. Whether this is normal or not is a little unclear. These others are pretty convincing. There's some weirdness here at the peak that looks a little odd, but this one's a little odd. But this is very compelling here. Okay, so that's just to sort of say that when you're doing these partial sums, the increments of a Brownian motion ought to be normal, because the Brownian motion really represents a lot of sums of steps, of small steps. So the increments, all the increments in Brownian motion ought to be normal. They ought to be independent of each other, because this was all built out of independent steps. So Brownian motion moves in that funny path, but the increments should all be normally distributed and all independent. Disjoint increments should be independent, and they should be normally distributed. And that's what Brownian motion is. Well, here's another weirdness. Here's to say something about that this is a stochastic process limit, and it's saying something about that when you plot, if there is a stochastic process limit, you get the limits for the plot. So if the stochastic process has a limit, now here's the stochastic process. Let me just explain what I've done here. I'm taking the random walk and I'm plotting it as I'm converting it into, first I'm subtracting the mean, so that's what we did already. And I've got this time, nt times the same. So I subtract the mean from each step, and I scale by something. And I suppose that this thing actually converges in distribution to something, s. And then I'm supposing that the range is going to be positive. I want the range of the limit to come out to be positive. In the case of the, if it was constantly 0, the range would be 0. But if it's not 0, then the claim would be that the plot of the original data goes to the plot of this, which is to say the plot is a plot of Brownian motion. It's not Brownian motion. Remember, the point I'm trying to make is a slight distinction. The plot is not directly Brownian motion. It's a plot of Brownian motion. What do I mean by that? I mean that the Brownian motion path that's naturally associated with that it's in the time all right. It's moving around in continuous time between 0 and 1. However, the plot forces the maximum value to be at the top and the minimum value to be at the bottom. So the plot essentially just rearranges the max-min, right? It just rescales it slightly. There's going to be a maximum value and there's going to be a minimum value, and it's made to be at the bottom and the top of the plot. And the point is, whatever the process converges to, the plot will converge to the corresponding plot. So the point of this is a sort of math statement. If the random walks, scaled version of the random walks, converge to Brownian motion, then the plot of the random walk will converge to the plot of Brownian motion. And that's what you're actually seeing. You're not seeing Brownian motion directly. You're seeing a plot of Brownian motion where it's vertically constrained to just fit in the plot. And that's all it's done, because time doesn't need any changing anymore. Okay? Well, overdoing that point. The thought is, what am I going to say now to make this coherent? Okay, one of the important things about the central limit theorem is that it's sort of universal. So in all those plots that we did were all for a very, very special case. We only considered uniformly distributed steps, and then ones that were first uniformly on 0, 1, and then uniformly on -0.5, +0.5. All steps were uniformly distributed. And then we got all this stuff. We got Brownian motion. That would be nice, but not very useful if, in fact, that property was restricted to uniform steps. Right? I mean, I only showed you uniform steps. If uniform steps led to Brownian motion, but exponential steps led to some other thing, that would not be so good. It wouldn't be very universal. So, as you recall from the central limit theorem is telling you these sums are approximately normal no matter what the distribution of the step is. That's the key thing. That's what invariance principle means. It means that limiting behavior does not depend on the distribution of the step. It holds for not all steps, but a very large class of steps. That makes it very powerful. So the central limit theorem you can use regardless of the distribution of the individual variables. You need the mean and variance. Okay. So now, in order to see that, you can make new steps with different distributions and see if you don't see the same thing. So you start with this uniform. Here's this uniform, and you take some function of it, and it gives you a new random variable. So you take some function f of the uniform, and you produce a y. And then as x, you subtract the mean of the y. So it's centered. So we made it centered. Get new centered random walk. What should we see now? I guess I've been trying to tell you what you should see. You should see the same thing. That's what I'm trying to sell. I'm trying to sell that you should see the same thing. So here's 3 cases. This case, I've taken the logarithm of the uniform, I've taken the power of the uniform, and the negative power of the uniform. Now this first one, you should be able to show actually produces an exponential distribution with mean m. Because you just write out what's the probability this is that, and you take an exponential of both sides, and you'll see it's an exponential distribution. So this case 1 is a way of explicitly constructing an exponential random variable. These other cases produce other random variables, different ones with different distributions. So these are, one way of thinking about it is I start with uniforms. I generate I generate a vector of 10 to the 6 uniforms in one line, right? And then I apply this f to each of the uniforms, element by element. So I got a vector of these, whatever they are. There's some random variable with some other distribution. This happens to be exponential of mean m. But it doesn't matter, it's something. And it's no longer uniform. Right? Okay, so whatever it is. Now, there it is. We're going to plot these. They shouldn't be. I guess we're doing, here's case 1 and 2. So this is 10,000. So here's, this one's going up, this one's going down, this is blah, blah, blah. But it's the same sort of, this is case of 10,000. It looks a little different because only the primary difference is on this page we're plotting 2 by 2, 4 instead of 2 by 3. So the boxes are, rectangles are a little different shape because it's 2 by 2 instead of 2 by 3. But otherwise, it's the same thing. And it didn't matter now. The distributions are different, and you see exactly the same thing. It's rescaled. All this stuff is rescaled. It's just Brownian motion again. It doesn't matter what the steps were. So the individual steps, the stock market prices surely are not going to be uniform, and that has nothing to do with the final thing you see. Okay. So, you're seeing Brownian motion, but these are just plotting random walks. When you read Ross starts by doing the mathematics of this, what you see. Ross starts chapter 10 by saying, suppose you have a random walk. Suppose they have, the steps are short in time, and suppose you make the steps quick in time, and you make them small in magnitude, and you do that in the right way, what happens? And he shows you get a limit. Well, that's what the plot does that for you automatically. Okay, well, we're going to end on a contrarian note, just to make sure that I, as usual, I'll leave you in a state of utter confusion, right? As usual, okay? With the only saving grace is lunch, which comes to save you just as you're staggering away. So, but this is actually the very interesting part. So this is mostly what the book is about, so it's hard to resist this. The exception makes the rule. So actually in that last plot, which I'll go back to, we only considered, come on, you can do it. We only considered 2 cases. This is cases 1 and 2, so I'll go back to this. Here's case 1, logarithm of the uniform. Here's the power of the uniform for p equals 1/2 and 3/2. And down here is the negative power of the uniform. Now, why is this third case a little strange? Just look at this. What's going to happen? What kind of values are we going to get? You could get some pretty strange values here. The point to consider is the uniform is between 0 and 1. The log of the uniform is always negative, right? But then we put a minus sign to make it positive. However, if the uniform is very small, right, the logarithm is going to be very big, negative. So this could have very big values, just like the exponential distribution. But it's not very likely. Now this one, on the other hand, is a little different, right? It's 1 over the uniform to some power, right? So therefore, if it's the reciprocal of the uniform, it's maybe 1 over a small value. So the thing to realize when you look at this third case is that these values might be big because it's a reciprocal. It involves a reciprocal of a number that is less than 1 and could be close to 0. Okay, so that's... So, anticipating myself, we're going to look at case 3. Okay? We're going way... Here we are, back to uncentered random walk of this thing in the case of 3 halves. So it looks like the earlier plot. This looks like this is uncentered. This is uncentered. We went way back to the beginning, repeating the beginning where we don't center. So remember what we saw before. How does this differ from what we saw before? At some level, it should look just the same. It's going to align, right? It's going to align just like before. Uncentered uniforms goes to align. This goes to align. But what you should see here is this doesn't go as fast. Before, at the very beginning, by 100, you didn't see any of these breaks. And at 1,000, it was clearly aligned. But now, this is pretty good here. It's a little bit funny at a couple of points, but the line is good at 10,000. But here, at 1,000, there's some jumps here. Well, I mean, everything jumps at 10, right? This is a little, here you see there's a kind of a big step here. But now these random variables no longer are bounded, right? We've done this. This is 1 over u to the 1 over p. It's a complicated thing. Okay, and then this thing's got, this is going to, the picture tells you that, again, like the first case, this is going to align, but it isn't doing it as rapidly. Okay. So, now we do the other case. This is just the uncentered random walk where we take the smaller p, u to the minus 1 over p. So this is 1 over the square root of u. Right? 1 over p. No, 1 over u squared. 1 over u squared. So if u is small, u squared is even smaller. And it's 1 over u squared, right? So if u happens to be small, this is 1 over u squared. 1 over u squared is going to be big. So this is what you get. You plot it. You plot the uncentered thing, and it looks like this. The sort of observation would be, this is kind of, the naive observation is actually extremely important. The naive observation is this picture isn't the same as the first picture. There's something different is happening here. I mean, this, remember, is just partial sums, is just a random walk. The steps are 1 over u squared. You can do this. You generate a random vectors of uniforms and take 1 over u squared. Just take 1 over u squared. You got a whole vectors of 1 over u squareds, right? They're all independent, identically distributed, 1 over u squared in each one. Cum sum the vector. You got a vector of cumulative sums. Plot it. This is what you'll see. If you plot every other case you could think of, right, lots of them, right? Normals, exponentials, they'll all look like the other one. Now, you plot this, and it looks totally different. And you could consider, I hope I'm doing this well. Okay, here's, the thought was before is that you can do the same experiments, whole 50 experiments of repeating 10 to the 4th, doing 10 to the 6th, doing all that stuff. They'll all look like this. Okay, but then here's the explanation. The explanation is that this random variable we're looking at has, the one we just looked at has infinite mean. It violates the conditions for the law of large numbers, and it violates the conditions of the central limit theorem. This random variable u to the minus 1 over p is, you know, if I take reciprocals, it's this, and here's the tail probability. So it has infinite mean when p is less than 1 and infinite variance when p is less than 2. So in the first case, it had finite mean but infinite variance, and in the second case, it had infinite mean. The theorems tell us, in a kind of boring way, the central limit theorem requires a finite variance in order to get the normal approximation. The law of large number tells you need a finite mean to get this law of large numbers. Almost always those conditions are satisfied, so you just sort of ignore them. But it's easy to make random variables that are perfectly proper random variables with infinite mean and infinite variance. 1 over u squared has infinite mean, and of course infinite variance. So the law of large numbers doesn't hold. But I mean, it's easy to see. It's much more interesting than reading the book. You know, it's kind of, you can easily do it and you can see it. Now, if you go back to the centered random walk in the case where it has finite mean but infinite variance. So it was converging slowly. We can see what we get. This is the case where the was going to a line but not very fast. Now you see something. This doesn't look like Brownian motion. So the thing you should see here becomes sort of clear. It's mostly going down except for jumps up. You're seeing it's kind of got a weirdness. It's going down except for, you can begin to see here, it's going down and then there's jumps up. But this picture looks different than the previous one. And this is now centered, but in the case where it had, so this corresponds to the case where the mean exists, so the law of large numbers held, but this variance doesn't exist. So this thing, this limit is not Brownian motion. And it doesn't look the same. And there's a different theorem for this case, because it's, but there's another, in all these cases where the mean and variance don't exist, there's analogous, there's whole probability books full of alternative limits in these cases, which give you different scaling, different limits, everything's different. But regularity all the same, which we may see here. Looks like we're going to see this. I guess we'd be doing repeating 10 to the 4th would be the thing to do here. Here we are. Here's 6 cases of 10 to the 4th. This is nice. So just like before, you can really get into looking one plot at a time. You see this one, boom. This one jump is a whole story. So this one makes you think, oh, surely it's just going down. This one, well, wow, boom, one big jump. This hardly any jumps. I guess, presumably we'll do 10 to the 6th. So 10 to the 4th and 10 to the 6th are interesting. Yeah, I don't know if it's entirely convincing. So the thing you're supposed to see here is that the figures you see, the plots, we've kept the situation the same, we only changed n. The plots look the same. They're self-similar. The plots with u to the minus u, 1 over u squared steps look the same, and they have these weird jumps. And the distribution of the process is not going to be normal and increment. It's going to have some other thing, because the central limit theorem isn't going to hold. But there will be regularity. So if you do a lot of steps, the story, these, if you do 10 to the 8 and so forth, all these plots are going to look the same as each other, but they're going to not be Brownian motion, because you don't have the conditions. It's something different. Now, this is repeating the case of the uncentered when we didn't even have a mean. So this is the case, the really bad case. It's uncentered. This is 1 over u squared. The previous one was 1 over u to the 2/3 or whatever. Yeah, this is 1 over u squared. So here it's just going up, because it's 1 over u squared, and you got a big value there. You get, the thing is driven by, and as you might expect from looking at this, that no matter how big n is, it's going to always look like this, which means that unlike Brownian motion, individual steps in these cases are so big that one step up is equivalent to all this thing, is of the same order as the total rise. The jump from the left end to the right, it's going up, but notice that the amount up is, in this case, dominated by this. Well, it's not obvious. You might think from this, it's not clear what's going on. You might think as you start doing n equals, let's see if we get n 10 to the 6th. You might think that it's eventually going to become one jump. It's natural to debate that if you increase n, what will you see? And one view is, well, the jumps are going to disappear, and the other view is that jumps are going to dominate. Here's 10 to the 6th. This ought to convince you that neither of those are correct, that this picture you see is the limit. It looks like this, that there are jumps. The jumps are very, very important, but there are other things too. And it'll always be like that. And if you made n 10 to the 100 or whatever, it would still look like that. Then you would have precision trouble, for sure, if you made n equals 10 to the 100, but you'd have trouble. These are called Levy processes, these things we're looking at here, which are processes of which Brownian motion is a special case, but only a special case. But you see the same kind of regularity, so that mostly you get Brownian motion, but you could have these other things. So this becomes a kind of current hot topic of, I mean, it's an old topic in probability, but in stock and finance, this is kind of a recent topic where you think that the stock market is very volatile, and you want a model that captures some of the volatility. So you start doing things like using Levy processes that have jumps to deliberately incorporate model features that represent what you think is happening in reality. So actually these things, these more general processes that are no longer Brownian motion, are things people are interested in when they think that the individual jumps play a role. That in fact in a large picture things don't happen smoothly. Brownian motion's pretty rough, but it's continuous. But this stuff, these Levy processes, it's making its movement largely by jumps. And so the question is, in a stochastic process that's maybe mostly continuous, you're thinking, is change happening continuously, or is it happening abruptly? And these are alternative models for that. Sorry, I'm reading this. So is this true? Okay, this is conclusions. Conclusions. The thought is, the first coin is good, okay, but if you just plot the stuff, if you just plot these random walks, you can see the statistical regularity. When you plot the random walks, you'll see the regularity, and then the math is sitting there to tell you that under blah, blah, blah conditions, that's happening. But you actually see it directly by plotting it, so that actually the simulation is very good to experience and see the statistical regularity. And the limits, the stochastic process limits, the math are explaining it. They're telling you that under such and such conditions, this sequence of stochastic processes is going to converge to Brownian motion, or a Levy process, or stable process, and therefore when the sample size is large, it's going to be the same as this limit process. And so it's telling you, with the right math, will tell you that you should see this. And it will be different pictures in different circumstances, which is where you want to get to at some point. Surely, this for curiosity is the alternate plot of the density. This is extra stuff. This is what you do when you do the density plot in the irregular case. It doesn't look normal. It looks actually badly not normal. It doesn't plot well. But anyway, that's I guess that's the L time. So chapter 10, this is chapter 10, so not this last stuff, none of this stuff with the jumps, but Brownian motion is chapter 10. And that's what we're finishing with.